Hi, so my name is Sam Procter. I'm the principal investigator on a research project here at the SEI called Formalizing and Automating the System Theoretic Process Analysis, or STPA, with Robustness. And if STPA and Robustness are not familiar terms, no problem. We're going to be talking about all of that in this short sort of overview talk. So the area that I work in is safety analysis. And the problem is, if you have ever built a critical system, one of these systems that is vital to the mission, or it's safe and continuing operation, is responsible for preventing injury or death to humans, or even if its failure would just cost an unacceptable loss of money, you know that it's slow. Safety analysis is slow. It's challenging, and you don't really know when you're done. A lot of times it's we had 2 weeks to do safety analysis, so we just analyzed it for 2 weeks and now we're out of the time, but we think we did okay. That is sort of unsatisfactory, right, for a number of reasons. And so we wanted to see if we could improve safety analysis by integrating some foundational computer science techniques. So if you're building a phone app or a web page, a lot of times you sort of build it and you release it and out into the world and you see how it does and you iterate from there. And this iterative development process is very successful. For critical systems, it's a little bit more challenging because you don't want to be the first one on an airplane where we haven't sort of seen anything about its safety. So instead we analyze critical systems as they're being built for safety and related concerns. A lot of times, these analyses take the form of what are called hazard analysis techniques. There are a number of hazard analysis techniques out there. You might be familiar with some, like the failure modes and effects analysis, or failure modes, effects, and criticality analysis, FMEA, or FMICA, they're sometimes called. Fault tree analysis is also very common. In this project, we use the System Theoretic Process Analysis, or STPA. And if you're familiar with STPA, I think this talk will be interesting. If you're not, I have the world's shortest overview. This is not a real training or anything like that. It's really just sort of context for the project. So the first step in STPA is to identify what aspects of your system you control and to draw a line around those. That line is your system boundary. Everything within it you control, and everything outside is the environment. And you're also, in this first step, defining the purpose of the analysis. So these are the losses or accidents that you want to avoid. Most of the time this involves the system interacting with its environment. So if we're building an airplane, we might control the hardware, we might control the software. We don't control the people on the airplane. We can give them instructions, and they may or may not follow those. And we want to keep them as safe as possible. So once we have our system boundary, we will go ahead and model the control structure. Now, the control structure in STPA, the sort of concept, borrows a bit from control theory. So you have controllers sending control actions, what we say down the abstraction hierarchy, to actuators which affect some change on what are called controlled processes. Then those controlled processes, it's modeled as sending feedback back up. Of course, in the real world, it may be more of sort of a pull from the controller than a push from the controlled process. And by that I mean, if our airplane controller needs, say, the airplane's speed, it's not so much that something is sending speed information back up as it is that the controller is reading some sensors and then deriving from that some speed information. But it's helpful to think sort of in an abstraction where we have higher level components, which we term controllers, sending controlled actions down the abstraction hierarchy to lower level components, who themselves might be controllers for even lower level components. But then they send feedback back up. And that lets the controller sort of estimate the state of the world, the state of the controlled process, and make decisions based on that. So I will say, all of this abstraction hierarchy can scale to a number of levels. You can actually have multiple system boundaries. So, you might have a boundary around your software, and then a boundary, again, around your software plus your hardware, and then a boundary around your software, hardware, and human operators. STPA scales to sort of arbitrarily complex systems and has been used to successfully analyze some of the most complicated and critical systems being built today. For this talk, we're going to keep it real simple. We're going to have one system boundary. We're going to have a real simple control structure. once you have the first two steps completed, you're ready for the third step, which is probably where it starts to get really interesting, because you identify which of these control actions could be provided in an unsafe way. And the way that you do that is by filling out an unsafe control action table. So the unsafe control action table is going to have all of your control actions as rows, and it's going to have some guide words that are provided by the STPA technique as columns. And you think about the interaction of the guide word and the control action, and whether or not that would violate a safety constraint, cause a hazard, and ultimately trigger a loss or an accident that you defined in the first step in the purpose of the analysis. So to make this all a little bit more concrete, let's talk about the brakes on an airplane's wheel. So your airplane's on the ground, you're rolling either for takeoff or for landing, and the pilot has the ability to apply the brakes to that wheel. So the control action, one control action, of course, would just be to apply the brakes, to hit the brake pedal. So this third step of STPA will ask you, okay, so you have your brake control action, and then we have some guide words which will not change. The way the control actions are, of course, system specific, to say, what happens if you don't provide the brake action whenever you should? Is it possible that would be unsafe? And I think this one's pretty obvious. Yeah, right? If we don't engage the brake as we come into land, we're going to overshoot the runway and put everybody in the plane and some people on the ground at risk. The second guide word is what happens if you provide the brake action when you shouldn't. It doesn't really matter, what the specifics are. Just, is there a time when you should not be applying the brakes that if you do, it will be unsafe? And this one's maybe a little less obvious, but I think the answer is yes, right? If you are about to take off and the brakes apply suddenly, you might be going too fast to stop by the end of the runway, but too slow to achieve a safe takeoff. And so, again, you run this risk of overshooting the runway. Then the third column is if you apply the brake too early, too late, or if it were a sequence of commands, which this one isn't, so it's not applicable, apply those out of order. So yeah, if we come into land and we apply the brake, but we do so too late, we could still overshoot the runway. It's sort of a timing critical thing that shortly after you're on the ground, you need to be applying the brakes. And then the last one asks, okay, what happens if you start applying the brakes at the correct time, but then either let off of them too early or hold on to them too long? And again, this could be unsafe. If we disengage the brake before we have a safe taxi speed, we're going too fast to taxi, but probably too slow to take back off. So filling out this table is all of step 3. Then in step 4, you would identify ways that these come about. But of course, identifying those loss scenarios and then ultimately updating your system according to what you have found can be very challenging. And there can be multiple entries in this table. Just because we have an element in each cell doesn't mean that we've found all the problems. There can be an arbitrary number of them. Also, this is kind of hard. Like it's a little bit easy because we're working on such an abstract system here, but in general, this is a tricky problem. And so what I wanted to look at in this project is using what are called formal methods, which are mathematically grounded, precise computer science techniques to improve the speed of this, to improve the accuracy of this, and maybe even provide some sort of confidence to the system analyst that they have found, if not all of the problems, many of the problems, that they have some level of confidence that they have a reasonably complete hazard identification. So what we want is to go from models of our system to a full analysis. And we're going to use a number of technologies to do that. The first one is SysML. If you have done any sort of model-based systems development, you're probably familiar with the systems modeling language. SysML, in this case, there are a number of tools that you can use to edit it. We're using Cameo Enterprise Architecture. This work is developed as a plugin to 2024X. If you have used Cameo Enterprise Architecture, that may be meaningful. If not, just know that it's one of the more popular system modeling environments. And then we're also going to be using, like I said, STPA, but there is a modeling language for risk analysis and assessment, RAML, the risk analysis and assessment modeling language, which is an extension of SysML, and it provides support for a number of popular hazard analysis techniques, including STPA. So what we want is to be able to go from a carefully modeled system to some idea of the unsafe control actions table for STPA. Now, the airplane brake system that I described earlier, even though it's sort of simplified, is probably still too complicated for a short overview talk like this one. So instead, we're going to be talking about a water tank. And our water tank has one safety risk, which is that it can overflow. We want to avoid that. It might also run out of water. That's more of a functional problem, not really a safety problem. So we're not going to be analyzing that. But the way that we hope that this tool could work, the way that we have designed this tool to work, is that you model your system using a state machine diagram, if you're familiar with SysML, and you model your environment or your operator, in our case, using an activity diagram, which is another diagram type in SysML. And the idea is that if the system is operated according to the instructions, then there is no safety problem. So what does that mean for our water tank? Well, our water tank, we'll say, is providing some amount of water at all times. It's just draining. But it's connected to a pump which is able to refill it. And when that pump turns on, the tank will stop draining and actually start filling. And then as long as you don't do anything else, it will continue filling until you turn the pump off, at which point it will go back to draining and it will continue draining until you turn the pump back on. So you can do this all day long. In order to fill the tank, we provide instructions to the operator to say, okay, go ahead and turn the pump on, wait, and after you've waited some arbitrary amount of time, and you could specify this. STPA a lot of times has this concept of sort of Goldilocks time, too little, too much, just right, and we follow that here. So you wait some amount of time, and maybe the tank is half full. You wait the same amount of time, now the tank is full. You turn the pump off, and you're good to go, you're done. So what we want is to be able to generate an unsafe control action table that would find some safety issues with this. And in fact, there are a couple that sort of jump out, right? So using our guide words from earlier, if we provide the turn pump on command, is it possible to overflow the tank in a particular system state? And the answer to that is yes. And so the way to read this is a system trace through your machine that if you then have this combination of guide word and control action, you'll violate your safety property or what you want to avoid, overflowing the tank in this case. So if we turn the pump on, we wait and the tank is half full. We wait and the tank is full and we turn the pump off. But then we inappropriately provide turn the pump on, we turn the pump back on, then we're going to overflow our tank. Similarly, if we turn the pump on and we wait so it's half full, we wait so it's full, and then we do not provide the turn pump off command, then we're going to overflow our tank. And so what we want is some automated way of building this table from these models. And that's what we've built in this project. The way we do that is with a new system property that has been sort of conceptualized, and some tooling to analyze systems for this property have been developed here at Carnegie Mellon by some of our collaborators, Dr. Insik Kang and his SOTA lab. The property is called Robustness, and without sort of getting into the weeds, the definition that I have here of robustness is that a system we can say is robust with respect to a particular property and a particular set of environmental deviations if it will satisfy that property even when the environment exhibits those deviations. So to translate this sort of to our water tank, what that means is that the system is robust with respect to not overflowing in the context of some sort of missteps by our pump operator if the system will not overflow even when the operator does some things that are incorrect. So what we do is we sort of map some of the concepts in STPA to the foundational concepts used by this robustness technique, right? Like our system becomes the machine, M, in the formalization used by the robustness. The environment is the environment. And then we look for, robustness is calculating a set called delta of environmental deviations. So these are missteps by the operator. So all the way that the operator can sort of fail to follow the instructions that we give them. And then we identify which of those missteps lead to the tank overflowing, because those are the potential safety issues. So there are details in this paper. This is not anything that the user would ever need to understand. This just sort of gives an idea of underneath the hood what we're going to do. So the way that this works from the user's point of view is exactly sort of what I described a minute ago, that we go from these SysML models to this STPA table. But under the hood, there are a number of transformations that occur. The first is that the SysML models get translated to a different language called the temporal logic of actions, or TLA+, that is much more precise and amenable to the sort of formal analysis that we need to do. Then those TLA plus files are provided to the CMU developed tool, it's called Fortis, that calculates a system's robustness. And we have, as part of this project, modified it a little bit, modified its output format a little bit. And so what it will end up producing are pairs of traces through the system or through the machine. So it will first find a bad trace, or a trace that leads to violating our safety property. So for our water tank, one of these would be turning the pump on and then waiting 3 times instead of just 2. Then it will say, okay, I have an unsafe trace. What might the operator have been doing when they did this? Like, what is a very, very similar trace that does not violate our safety property? And that we call a good trace. So in this case, turning the pump on, waiting 3 times, very similar to turning the pump on, waiting twice, and turning it off. So now we have a trace pair. One is unsafe, one is safe, and they're very similar. We now run this through a classifier, which turns it into an unsafe control action from STPA. So the way we do this involves an algorithm that is similar to what is used in a spell checker, right? Where you have a misspelled word and a very, very similar correctly spelled word. And so depending on whether you add an action, remove an action, transpose them, substitute them, there are a number of sort of edits, they're called, to these traces, we can determine the correct guide word to be associated with the unsafe control action. So once we have that guide word, we can figure out sort of the other elements. If you look in the STPA handbook, an unsafe control action has 5 elements. We can figure all that out, and now we have all the pieces necessary to build this table. And so we reformat this into STPA using that risk analysis and assessment modeling language, or RAML. And so we get in Cameo, in our editing environment, a table of unsafe control actions that has been generated from our SysML. So that is sort of the short overview of the Formalizing and Analysis STPA with Robustness, or Phaser project. This is the team. Keaton and Lutz are here at the SEI. These are our CMU collaborators. If you want more information, I have a link here. You also should go ahead and email info@sei.cmu.edu if you are interested in this. And that could be sort of if you're academic and you want to extend it, or if you are in industry and you want to apply this, or if you have questions, or if you think, this looks neat, but I'm not sure it would work. That is the sort of thing that we want to hear. This is really a sort of an early research project. This is provided as a plugin to Cameo Enterprise Architecture, but that plugin is something that we would be interested in sort of modifying based on how people want to use it, whether that means that they have sort of different models than what we anticipated, or they want to check different sorts of properties. We really are looking for collaborators to talk about what that might look like. So yes, please reach out if this sort of piqued your interest, or if you have any questions. And thanks for listening to me talk about STPA and automation.